In the previous lesson, you examined the way in which you can determine the rate law for a reaction by doing an initial rates experiment. And in the initial rates experiment, we were changing the concentration of certain reactants independently of everything else and monitoring the effect on the initial rate of the reaction. And the initial rate of the reaction is measured at time zero. So if you imagine a concentration versus time graph, something like this, the initial rate is what occurs right at the beginning of the experiment. So it's the instantaneous rate of change at that moment. Now, this isn't always the most practical way to study the rate law of a reaction. And so what we're going to do is look at a graphical method for determining whether a reaction is first, second, or zero order. And what we're going to be doing in order to do that is completing what is called the integrated rate law. Now the math gets a little bit complicated, but we're going to avoid the complicated part of the math and we're going to focus on the linear functions that are derived from the complicated math. So first of all, what we need to do is talk about what kind of an experiment this would apply to. The kinds of experiments that we will do are ones where we will monitor the concentration of a reactant or product over time. And as we monitor the change in concentration with respect to time, we'll collect data, and that data will be used and applied to various graphs in order to make a decision about whether it's first, second, or zero order. Now, the ways in which we will collect this data will depend on the type of reaction. So recall that at the very beginning of our discussion of kinetics, we talked about the various ways that we can monitor the change in concentration of a substance over time. So for example, we can monitor the change in the mass of the system, we could monitor the change in the pressure of the system. The experiment that we're going to do, we're actually going to do a titration every 10 minutes in order to determine the concentration of a reactant in our system. Now let's look at the derivation of the graphs that we need for our analysis. For a first order reaction, you know that the rate is equal to the constant times the concentration of A raised to the power of 1. That's first order. Now, if we look at this as a rate of change, we're monitoring in rate the change in concentration with respect to time. So that's what dA over dt means. Now this has a negative sign because, as you know, if we're studying a reactant, its concentration is going to be decreasing over time, so it's going to have a negative rate. Now we're going to look at concentration in a more simplified symbol. We're just going to use C. So we can also say that rate is equal to dC over dt, and it's equal to Kc. Now this is where some complicated math happens, and we're not going to worry about the complicated math. If you want to review the complicated math with me, it's integration that we're doing, and integration is the opposite of taking the derivative. So unless you're in AP Math, you will have not learned how to take an integration. You're still in the midst of learning how to take derivatives. So with some discussion, I can show you how it works, but that's not really the focus. Okay, what we need to do is kind of think of, okay, some math happens, and after integration, this is the relationship we obtain. Now this is going to be a new symbol to people. This is ln. And ln is called the natural logarithm. So you know about logs because you have studied pH. Just gonna do a little side note over here. With logs, when you put in your calculator log of 2, what you're asking your calculator to find is 10 to the what is equal to 2. So when we're looking at lns, okay, I can look at ln of 2. And what I'm doing here is I'm simply looking at a logarithm that's not base 10. When we write log, what we're not writing in here is that this is a base 10 log. So it's 10 to the what is equal to 2. Ln is what is called the natural logarithm. Okay? And when we type into our calculator ln 2, what we are saying is e to the what is equal to 2. Now e has a special value, and there are many things in nature that decay naturally according to this logarithm. The value for e is 2.718. So when you put into your calculator ln of 2, you're asking your calculator to tell you what e needs to be raised to, or what 2.718 needs to be raised to, in order to equal that value. So for your purposes, what you need to be able to do is find ln on your calculator. It's below the log button. Okay, and the inverse of log is e to the power of. So just like log has 10 to the power of as the inverse, ln has e to the power of x as the inverse. So this is going to be similar to switching between pH and concentration. That's our little side note about ln. Okay. What we want to do is look at this equation and then look at this rearranged version of the equation. So what I did was I moved the ln c over to the right-hand side. And what we want to do is connect this to the equation of the line y is equal to mx plus c. You can see the connection here. Y is our ln c. So let's look at what graph we're dealing with here. Ln of c. The slope of this line is negative k. The x value is t. And the intercept is ln c naught. So what this integration gives us is the equation of a line for the graph of ln c versus t. And ln c versus t, when you have a first order reaction, ln c versus t gives us a straight line. The intercept, the y-intercept, is ln of the initial concentration, and the slope of this line is negative k. This is what's important to us. It's what you'll see in a minute when I summarize and emphasize this again. We want to take the data that we collect from the lab, so we're going to collect data of concentration versus time, and we want to know if this is a first order, second order, or zero order function. So what we want to do is take this data from the experiment and put it into this graph. So I'm going to take ln of each of my concentrations, put it against time, and if I get a straight line for that graph, then I know that the reaction is first order. So it's kind of like building this graph is a test for us. It's a test to see if the reaction is first order. If it does happen to be first order, we're also going to have the rate constant. And the rate constant is going to be the negative of the slope. Let's look at a similar scenario for a second order reaction. So for second order, you know that rate is equal to the rate constant times the concentration raised to the 2. Similarly, that's going to be the change in concentration with respect to time, so we can put it as dA over dt. We're talking about a reactant, so that's why it's negative. And if we let the concentration be C, then we have dC over dt is equal to kc squared. Okay, so this should actually just be C. Now, again, if you want me to discuss the integration with you, I can. It's really not that necessary, but if you would like to, I can. When we integrate this, we are given this relationship. And when I rearrange this to put it in the form y is equal to mx plus b, I can see that for a second order reaction, there is another graph that will give me a straight line. This graph is different. The y value for this graph is 1 over c. The slope for this is k. The x value for this is t, and the intercept is 1 over C naught. So for a second order reaction, the graph that's going to give me a linear relationship is 1 over the concentration of C versus time. This time it's going to have a positive slope, and the slope is going to be K. So the next couple of slides will summarize this, and then we'll do an example. And once the example is done, hopefully this will become a little bit more clear as to how this is going to be used. Okay, so just to summarize, for a first order reaction, you're not going to have a linear relationship when you have concentration versus time. But if you take the ln of the concentration with respect to time, you'll get a straight line. This is the equation of that line, and the slope of that line is negative K. One important note for this is that nuclear decay is a first order process. So that's an important point because sometimes you're asked to study nuclear reactions and you're expected to know that they occur in the first order. To summarize a second order reaction, if you looked at just the concentration versus time, you're not going to get a straight line. If you look at ln of concentration versus time, you're not going to get a straight line. What you're going to get a straight line for is when you graph 1 over the concentration versus time. You get a linear relationship with the slope equaling K and the y-intercept being 1 over A naught. And this is really helpful because remember from our last lesson, what we were doing is trying to figure out the rate law. And when we solved for the rate law, we also determined what the rate constant K was. Now we don't need to really do much with a zero order reaction, but we can discuss it. So with the zero order reaction, we know that the rate has nothing to do with the concentration of A. Okay, so it's raised to the 0. So the rate is simply equal to K. And what that means is that over time, the rate of the reaction is not going to change. So when you look at a graph of concentration versus time, when the order of the reaction is 0, what you get is simply a straight line. And the slope of this line is negative K. Okay, the concentration of A is simply decreasing in a linear fashion. So let's look at an example because it's the best way to really put this together and see how you need to be able to manage this information. So in your notes, you have in the second example that I give you, okay, with the 2NO2 going to 2NO and O2, you're given the time and you're given the concentration of NO2. So what has happened here is an experiment was done, and every certain number of seconds, the concentration of the NO2 was measured. We can assume here that they measured the pressure, for example, and they converted that into a concentration. So the data that you're given is the time and the concentration. Now what we want to be able to do is determine whether the reaction is first order or second order in NO2. And we also want to be able to determine what the K value is. So let's just look ahead for a moment and look at the graphs that I've created from this data. If you look at the graph of concentration versus time, so this is the concentration of NO2 versus time, you'll see that over time the rate is changing gradually. So this is not a zero order function, we know that. What we want to know is if it's first or second order in NO2. So we need to test the data. If the concentration versus time was linear, then we would know that it's zero order. Okay? If not, then we need to check the next one. If ln of concentration versus time is linear, then we know it's first order. And if 1 over concentration versus time is linear, then we know that it's second order. So we need to manage this data. So in Excel, what I did was I took the concentration data and I took the ln of each value. So the ln of 0.01 is negative 4.6, okay, and so on and so forth. I also, in Excel, did 1 over concentration because it's easiest for me to just test both of these, ln and 1 over concentration versus time, and then I can make my decision. So let's look at the graphs that were produced. For the ln of concentration versus time, I'm showing you two different graphs here. It's the exact same data. The difference between my analysis here is what I've assigned the data to be. So in this graph here, which was my first graph, I forced it to be linear. So I added a trend line saying that I wanted it to be linear and I wanted it to show me the equation of the line. I also asked Excel to display the R-squared value. The R-squared value is a statistical value that really is showing me how close my data are to my trend line overall. When R-squared is equal to 1, that means that you have selected a perfect fit to your data. Okay, so when you see this, if you look at the data, you can see that it's not linear, okay, but you can also see it even more obviously by graphing the line and noticing that obviously it does not go through all of the data points. And my R-squared value is 0.9827. Okay, so this is not linear. So this means that this is not a zero order reaction. This graph up here that I'm showing you, all I did was took the same data, and what I did was I asked it to be an exponential curve. So I asked it to have an x squared. And you'll see that my R-squared value is closer to 1. And you can also see that this line actually fits the data better. Okay, so this is a better fit to the data, a secondary proof that ln of concentration versus time is not a linear function. Confirmation that this is not first order. Okay, the next graph, I'm looking at time and 1 over concentration. So my y values are 1 over concentration and my time is in seconds. This graph doesn't start at 0, 0. I've just scaled my graph so it starts at 99, so it's a little easier to see the data. And you can see from this one that it has a perfect linear fit. My R-squared value is 1. Okay, my equation of my line is given here. So this means that this reaction is second order. The other thing that's great is now that I've done the graph, I know that it's second order. Okay, so I know the exponent in the rate law for NO2 is a 2, but I also know that the K value for this is the slope of this line. So it's 0.5445. Okay. The units for this, I know because it's second order, are liters, moles, and in this case, the time unit is seconds. So hopefully you're feeling like you can use a different kind of data to determine the rate law of the reaction. That's what you should be feeling right now. This is just a different method for determining the rate law of the reaction. You're taking concentration and time data and you're testing it against the different graphs and making decisions from that. Now, because we have these linear functions, we can also derive relationships for what is called the half-life for a zero, first, and second order reaction. The half-life is the time that it takes for the concentration of the substance to reach half of its initial value. So this is a good visual here. Okay, going from this point to this point, that is one half-life. Okay, the number of green molecules here has been reduced to half. So that's one half-life. Okay, in this box I've got 8. I reduced to 4. That's another half-life. When I go from 4 to 2, that's another half-life. 2 to 1, that's another half-life. 1 to half, half to 0.25. Okay, so each is a half-life. Take the time that it takes to reduce the concentration to half of its original value. Now the half-life in a 0 first or second order reaction is going to be a little bit different. In your notes, I've taken you through the derivation of really it's a relationship that we're deriving just by rearranging. Okay, but what I'm going to do is actually walk through the steps here so you can follow along in your notes. What we have to work from is the appropriate linear relationship for the order of the reaction. So for a zero order reaction, we know that concentration versus time is linear. This is the equation of that line. A is equal to negative kT plus A naught. Now when we're looking at half-life, we're going to call it T half. It's the symbol we use for half-life, so it's the time of the half-life. At this point, the concentration of A is going to be equal to half the concentration of A naught. So what I've done from here to here is I've subbed this relationship into this one. Okay, so A is equal to half of A naught, and I've simply replaced the T with a T half to be specific. So what we want to do here to figure out what my relationship for T half-life is for a zero order reaction is rearrange this equation. Okay, so I've got half of A naught minus A naught is equal to negative KT half. And so this is negative a half A naught is equal to negative KT half. Okay, and to isolate T, I'm going to divide by negative K. So what I have is T half is equal to A naught over 2K. So if you know you've got a zero order reaction, you know that the half-life is equal to the initial concentration divided by 2K. So in this case, the half-life depends on the initial concentration. For a first order reaction, the linear relationship, it comes from ln of concentration versus time, and it's got a negative slope of K. So this is the equation of that line. Rearranging that to ln A minus ln A naught is equal to negative KT is what we did in the first step. Now you'll remember that when we have, for log rules, if you're subtracting, so ln A minus ln A naught is the same as ln of A over A naught, and that's equal to negative KT. When we're looking at the half-life, that's going to be the point where the concentration of A is equal to half the concentration of A naught. So I'm just going to do a little side thing over here. So if I've got half of A naught over A, okay, so I'm taking this expression here and applying it for my half-life, that is really just 1 over 2, right? Because A naught simplifies. So what we have here when we're dealing with the half-life, we've got ln of 1 over 2 is equal to negative KT of the half-life. If I move the negative over, okay, negative ln of half is equal to K times T. Now negative ln of half is actually equal to ln of 2. And the way that that works, you can check your calculator if you would like to. So if you enter into your calculator negative ln of half, okay, and ln of 2, you'll get the same number. Okay? And the reason for that is using log rules, so I'll show you over here. So if you've got negative ln of 1/2, that's the same as negative ln of 1 minus ln of 2, right? Because we've got a division there. So then this is negative ln 1 plus ln 2. And ln of 1 is 0. Ln of 1 is 0, so we're left with ln 2. Okay? And so we've got that relationship, and then I move the k over, and that gives me the t-half. Now again, do not panic if the math is over your head. It's not really the math that matters. It's this relationship in the end. And you can, if you'd like, you can always rely on knowing the relationship and deriving it from first principles using math, or you can know what the relationship is. Now, one of the things that's particularly special about a first order reaction is that the half-life of the reaction depends only on the rate constant. Okay? It's independent of the initial concentration. And it's inversely proportional to the rate constant. Okay? So the higher the rate constant, the lower the half-life. In this example, it gives us that the rate constant for the transformation of cyclopropane to propene, a first order reaction, is 5.40 times 10 to the negative 2 hours to the negative 1. And it asks us for the half-life of this reaction. So we know it's first order, so half-life of the reaction is simply ln 2 divided by k. So it's ln of 2 divided by 5.4 times 10 to the negative 2 hours to the negative 1, and we get 12.8 hours. Okay, so that means that half of the sample will have reacted after 12.8 hours. Now in the second question it asks, what fraction of cyclopropane remains after 51.2 hours? So if you want to know what is left after a particular amount of time, what you need to do is look at the linear relationship. Okay, sorry. Okay, so this is the linear relationship for a first order reaction. We know the rate constant here. And we know the amount of time that's passed that we're studying. And what we want is we want to know the fraction of propane that remains. So really what we're looking for is the relationship between the concentration of A and the concentration of A naught. So if I move, I've got ln of A, if I subtract ln of A naught, that's really ln of the concentration of A over the concentration of A naught. So I can figure out the relationship between the two. And I've got my negative KT here. Now the inverse of the ln is e to the power of. So if I want to solve for this fraction of A divided by A naught, I need to take e to the power of. I'm just going to put answer here because I don't have the value written down. Okay, that's going to give me A over A naught. And what you find here is that the concentration of A is equal to 0.062 0.99 times the concentration of A naught, okay, which is the fraction of A that we have, the fraction of A naught that we have left over. Okay, so you can do a similar example for what remains after 18 hours, and you get 2.64 of A naught. For a second order reaction, okay, we know that it is the graph of 1 over concentration versus time that's linear with a positive slope. And this is our function that we have. If we rearrange that to 1 over A naught 1 over A minus 1 over A naught is equal to KT. And then we substitute in our relationship for the half-life. So we're looking for K of T half. At this point, the concentration of A is half of the concentration okay, we're looking at 1 over half of A naught, which is really the same as 2 over the concentration of A. So what we have here is 1 over A naught is equal to K T half. So we have the half-life is 1 over the concentration of A naught times K. So this is our relationship. Okay, so if you're comparing 0 to first to second order, what's important is to understand the relative dependency on the rate constant and the concentration, the initial concentration. So for a second order reaction, it's inversely dependent on both the rate constant and the concentration. Okay, so what I'd like you to do at this stage is pause the video, okay, and work through these two examples, okay, and then check them with me. If you look at the bottom of the page where you see these examples, you see a chart that is summarizing the important features that we have studied in this lesson. So for 0, first, and second order reactions, it tells you what the basic rate law is, what the important linear function is. So the integrated rate law is basically the equation of that line that is going to be appropriate for that particular order of reaction. It summarizes it nicely to show you which plot you need to get a straight line for that particular order. It tells you how to find the rate constant, and it also gives you the formula for the half-lives. Okay, so this is a great chart to keep track of all of the information that has been thrown at you, all these different equations from this lesson. So that's going to be your basic go-to chart. There is also another example. You should work through that example. It will help you to identify which relationship to use and how to use your calculator to go between ln and taking the inverse of ln. And that concludes our study of kinetics.